OK. Sorry about the delay. It took about, I think, 20 minutes to boot it. At least you will have a webcast. OK, so that's good. It's a friend's old machine that I hiked up the hill. It's about 7, 8 pounds. So good. OK, so last time we looked at the impedance formula and kind of went through several examples. And now we're going to do a few more examples of both the feedback with return ratios as well as the impedance calculations. And then from next week, we'll dedicate pretty much the whole week to two-port kind of analysis. So you kind of have a complete view of feedback. And then you'll be able to choose which approach you like the most. And then on the final, do whatever you feel like makes sense. OK. I wanted to, since we looked at the, OK. Since we looked at the topologies that last lecture, was Ri, R1, R2. Whereas here we have AV error and R out. We sort of looked at the input-output impedance of this type of series shunt amplifier. Thought I would show you a few kind of uses for this. Like one really nice use for this type of circuit is as the voltage regulator. And so you would put the voltage you want to have at the output here. Of course, there will be some proportion. In the ideal case, 1 plus R2 over R1 gain to get to the VO. And that the idea is that this feedback would keep this VO stable for some Z load, or it could be current as well, regardless of what's happening on the supply of this circuit, right? So if the supply doesn't have a really good low impedance, so the supply itself is not really a good voltage source, then then the regulator will sort of clean up whatever is happening here on the supply and minimize the ripple over here. So one example of how you would build this, where we sort of just explicitly show the second stage, is that, and we've done output stages already. So this will be your VDD. And then here you would have your feedback. And then here is the load. Right. Since this is common drain, it essentially has low output impedance. It's a good output stage. And what this feedback is supposed to do is that even if you have a large fluctuation here on the supply, the fluctuation here will be much smaller because it will be regulated. The amplifier will be trying to enforce this voltage to the output and isolate and only kind of get the current from the supply, right? So stabilize the output voltage, but just pull the current from the supply. An example of how you would build this with circuits could be, for example, your standard diff pair. And then from here we go out. And then to tie the feedback, something like this. Now, of course, the load will be attached to this point over here. So this, in this case, this will be VR. This will be V out, and this is VDD. Okay. So what's of interest here is to look at what is the R out of this amplifier. And the reason for that is that if I have some current I'm pulling down here, I/O, I want this V out, the delta in V out, will be proportional to delta in I/O times R out of the amplifier. The smaller the output impedance I have from the closed loop regulator, the smaller delta V out will be for large changes in delta I, right? So if this is big, this is small, then this will be small, right? So the loop, because it's shunt, we already know it's trying to lower the output impedance, and we can go and calculate really how much this quantity is going to get affected. Right? So we have our R out will be our R out of A equals 0 times, and then we'll have what we done last lecture, the Blackman formula, 1/1 plus return ratio, because it's a shunt output, so the shorted return ratio is 0, and open return ratio is actually the return ratio. So, okay. And then we also have the closed loop gain is A equivalent over 1 plus RR plus A0 over 1 plus RR. And in this case, we have both of these terms. We've done this before, kind of, and derived them all. So if you go in and kind of replace these things, so A closed loop is really VO over V reference. And then we can plug things in to do the derivation. So from here, 1 over 1 plus RR will be V0 over A equivalent plus A0 times VR. And then we plug this in into the first one. So R out will be R out of A equals 0 times V output over A equivalent plus A0 times VR. So now we're looking at delta V out is R out times delta IO. So we're going to plug this in here and get the delta V out is equal to R out of A equals 0 times VO over A equivalent plus A0 VR times delta IO. Normalizing, so, okay, this is, well, let's just call this for consistency delta VO because it's the output voltage. So we're really interested in the percentage change, and that is then R out of A equals 0 divided by A equivalent plus A0 ER times delta I0. Okay, this expression kind of tells you by how much the output is changing percentage-wise for any changes in the output current, and is called load regulation spec. there is another specification that you typically use with regulators, and that is how much does the output change as a function of percentage change in the input voltage. But input voltage meaning the supply voltage, what supplies all the supply that gives all the current to the regulator. And this quantity is usually very topology dependent, and the reason for that is that if you look at the previous slide, some circuit provides this VR. Usually it's some reference that you build, and we've done references kind of in the middle of the term, and you know that these references have some, it's some circuit that is attached to also the supply voltage and also has some power supply rejection, that any change in the small signal change in the supply will percolate out to a change in the reference. And then this amplifier itself will have some power supply rejection ratio, as well as the sort of the second stage, right? Or we can say that it's the whole thing, right? So this will be, any change here will just go through whatever is a closed loop gain of the amplifier to show at the output. So you will have that delta V out will be a closed loop times delta VR plus power supply rejection ratio closed loop times delta VDD. But then this delta VR would also be, hope you can see that, yeah, will be power supply rejection ratio of reference times delta VDD. Right? So this piece is kind of, depending on what the relative ratio of supply rejection are, one or the other will be important, but usually because you do have some loop gain here, or some closed loop gain in the amplifier, this piece is going to be more critical. So you really have to pay attention to what's happening in the reference for the line regulations. Okay. Now we're going. So far we looked at kind of maybe easy cases to sort of figure out the feedback, because mostly it was shunt from the output, so it's kind of more intuitive. I'm gonna, end the slideshow already. Okay, so we're gonna do it a little bit in reverse. Okay, so let's do an example, Wilson. Current source. And you're going to tell me first sort of what type of feedback this is. So let's try to figure out the R out quantity, which is what we are normally interested in current sources. So we kind of did this derivation already, but it was really brute force, kind of just going through the KVL, KCL of the small signal model, because we didn't really know how to analyze feedback back then. But now we should just be able to apply the Blackman formula as long as we can figure out what the loop really is. So let's say type of feedback. Maybe the first thing would be to see which transistor is really the controlled source, so to speak. So let's label them M1, M2, M3, or sorry, M2. Let's be consistent. Okay. So which one really represents kind of the gain? No. M2, yeah. Yeah, M2 indeed. Right, so M2 is producing the output current, right? Where's the feedback? What's being fed back? M1 is just a resistor, right? It's a diode-connected device, so it is part of the feedback, you're right. But M2 sort of generates current, that's the output, that's the quantity we would like to sense, right? So how do we sense it? Sense current in series. Yeah. Okay, so we sense series, so sense I/O, right? Okay, so what senses the current? Which element senses the current? Maybe turns it into something else. Yeah, M1 accepts I out and turns it into some voltage, right? And then that passes that voltage to M3, which then turns it into a current, which will then go and get subtracted from the I reference. Right? Okay, what is the what is R out when the gain is equal to 0? So active elements, we have in this situation, all that's left of M2 is really just the RO2. And then here we have 1 over GM1, right? There's nothing else. There's no current source. We just killed the current source. So the output is RO2 plus 1 over GM1, which is approximately RO2. Okay, so what is RR or of output open? There's a hard one and there's an easy one, depending on. When the output is open, what happens with current? Current is 0. So is there any feedback? Right? There's nothing to kind of pump into this M1 resistor. So therefore, you basically just open the feedback. Because remember, the output feedback is series. So there has to be a circuit that goes around, or the current goes around. And here we just opened that circuit. Right? So this RR of output open is 0. And RR of output shorted equals what? The normal RR, that's right. So let's see what that one is. In this case, we can open here, although in the book, you know, in other places, like everyone has their own favorite way of doing it. So if we open here, we essentially can add vtest. And then I'll just write this as 1 over GM1. So since this is open as well, there's no current flowing down here. So all the current in M3 is really just going between GM3 vtest and into the RO3, right? That's the current path. So our RR is then going to be GM3 times RO3. So we generate then the voltage. And then we go into just the source follower, which is GM2 minus 1 over GM3 over 1 plus GM2 times 1 over GM3. So this is approximately GM3 times RO3. So once we have this and we have our R out, so our true R out is then RO2 times 1 plus the return ratio, which is GM2 RO3. Okay. To spice things up a little bit, we can also do a bipolar version. And the reason why I'm saying to spice it up, because now you'll see that there's not quite the 0 and RR as partitioning between the return ratios. Right? Now both are something. So we're going to do this variant of Wilson, where we don't use the extra device to kind of shift down. Okay, let's label them. It's Q1, Q2, Q3, and we're going to get I out here. Okay, what type of feedback? So series is the output. The input, you're essentially using this as kind of a signal processing node, right, between the reference current and what you're feeding back. So this is the I error, which is the base on the transistor, right? So it's actually a shunt. Okay. So how does the small signal model look like here? Let's do R out. The sources are 0 is what? So what we see from here, still we get RO2, and then plus we have 1 over GM1 in parallel with RPi3, which we can kind of neglect, so it's approximately RO2. Now, the return ratios become a little bit more interesting. So open, we have an output open. What happens to the return ratio? What? There's still base current, right? So that's where the trick is, right? So you actually, if you cut here and you produce a V-test here, and you can close with RPi, this current is going to be GM3 V-test. Right? And it will go, because this is going to be open, it will go into the base. And then in the base, it goes through RPi. There's no current source. And it goes straight down into 1 over GM in parallel with RPi. Right? So it's essentially GM3 times 1 over GM. There is in parallel RPi, but I'm going to neglect that. So this is approximately 1. The return ratio is not 0, but it's not like super big. That's 1. And then return ratio of output shorted. Now we have the transistor actually with the full current source. So we still have the current of Q3 going and becoming the base current of Q2. Right? So we have GM3 V-test times, but now we have 1 plus beta 0, which is how the base current becomes the emitter current and goes into 1 over GM1 parallel with RPi 3. Right? And if you solve this, this will be approximately beta 0. So then our R out is going to be equal to RO2, and then we have 1 plus beta 0 over 1 plus 1. So that's RO2 times approximately beta 0 over 2. Again, beta 0 increases the output impedance from what normally it was as RO2. But you have to be kind of careful what you do when you look at the types of feedback and how the return ratios work out. Okay, let's do one more example. These are also with different type of feedback than we've done so far. So you'll tell me again what this type of feedback is. M1, then drives M2. Okay, so let's say feedback type. Any takers? The output should be easy. Yep. Good guess. Or. I don't mean guess in terms of real guess, but like, yeah, good answer. Okay, the question is, though, if I drew it like this, would you have thought, okay, this is what I was waiting for. Okay, does this change the type of feedback? This is what I did. No. But you would have gone and said, this is a shunt at the output. Okay? And when we do the output impedance, R out, how would you have done the RR, the return ratio shorted, of output shorted, or output open, right? You could guess that one or the other corresponds to the full return ratio, right? So if you open, then you could say, well, in a shunt, open is good. That's RR, right? But here, actually, open means you destroy the feedback, because feedback is series. Right? So I really wanted to make sure you guys get this, right? So we're going to go through the example, but
so just by looking at this, how do you know series versus shunt, given that you have a voltage and
so I'm looking how the feedback is getting passed, right? So the circuit produces current, and then, yeah, the current terminates on some load and generates voltage. That's fine. But that voltage is not used anywhere back, right? So what is being used is this current quantity that passes down, right? So therefore, the feedback is series, right? So okay, if it's a series feedback, but I open the output port in order to do one of the return ratios. So let's say I'm doing the RR or of output open, right? If it's RR of the output open, and I've opened the output, right? Then what's the return ratio? I erase this, right? Because I have my output open. Is there any current flowing down? No. So do I have feedback? I don't have feedback. So this is 0, right?
So it's series at the input because that current involves voltage across RF, and that's going to change the source voltage?
Well, yeah. So will be your feedback, and then this is sort of your V error, right?
So I feel like I could also make that look like a shunt in my head with current going through that middle branch.
You can't, because that would mean that the current has to come from the input. And then your signal processing is the input current minus the feedback current, right? That gives you the error. But here you don't have the input, right? So you're doing the signal processing on this loop over here, right? But we know that at the input, if you're doing it in a loop, you're really processing voltages, right? But you're sensing, in a loop, you're sensing current, right? That's this loop over here. Okay, so I just want to make sure that this doesn't confuse you, because as apparently does, right? But it's very critical thing to see that you don't get the loading confused with where the feedback is. Okay. Because if you thought, you could have thought that, oh, I see V out, I'm getting RL, so it's a shunt. And if it's a shunt, when I'm calculating the RR output open, then that must be RR, right? Because in a shunt output, I'm feeding back the actual voltage, so I do want that output to be open. But here, you're not really feeding this voltage VO anywhere. It's just being developed on some load, right? What you're feeding back is this IO, right? IO is here. Does it make sense? Okay, nice. Okay, so then the RR of output shorted would be what? RR. That's right. Okay, and then R out when actives are 0. So if I don't have a current source here, I still do have RO3, right? So I'll at least have RO3 plus, and then I'm going down, looking into here, what do I have? RS1. Well, you don't have anything looking up M1 because that's also an active path, right? All those I'm nulling down, right? Okay. Now, in reality, what I do have, if I don't want to ignore it fully, I actually do have RO1 here, right? So in reality, what I should be really writing is something like RF plus RS1 in parallel with RO1 plus RL1. Okay. If I really want it to be like fully exact. But this is likely much bigger than RS1, so even though RS1 is kind of big, but it would kind of fall off. Okay, so in this case, our R out is R out with sources equal to 0 times 1 plus RR, right? Because we have a shorted over the open. So, and indeed, it's like it should be the feedback does boost the output impedance because this produces current, and current current source should have a large output impedance, right? Okay, so in the remaining few minutes, let's just go back to the same circuit and do the A equivalent because we haven't really done it for this type of feedback. So for the return ratio, what we'll do is we're going to null the input, and we have the V test that we apply here. And then there's just a series of gain stages, which is not a big deal. I'm going to ignore sort of all the R naughts in this case pretty much because I'm going to assume that the load resistors are smaller as they should be. Okay, this is M3, M2. Now, what I'm seeing here, I have RF, RS1, and then whatever VT is seeing, which should be, let's say, 1 over GM1, I'm going to terminate here. and I'm measuring VR, right? So this is our standard return ratio thing. So let's maybe make this first, just so it's not confusing, return ratio. Okay, so our VR is equal to VT times GM1, which is the first stage, times RL1, then minus GM2 RL2. And then we have a source follower, right, which is GM3 times something over 1 plus GM3 times that same thing. And what we have here is RS2 in parallel with RF plus RS1 in parallel with 1 over GM1. Right, that same thing is here. And then once we are at that point over here, we have another voltage divider, which is 1 over GM1 in parallel with RS1 over RF plus 1 over GM1 in parallel with RS1. Here we can assume that this is just 1 over GM1, right? So this whole thing will become 1 over 1 plus GM1 RF. So then my RR is going to be minus VR over VT. So I'm not going to kind of repeat it. What is A0? We go back to the previous picture. If all the FETs here on this forward path have GMs of 0, because I killed my forward path, then what is the gain from input voltage to output current? Is there a path? No, there's no path yet. That's one of the nice things with these MOSFETs. They do have nasty quadratics when you have to do the biasing, but on the other hand, they save a lot of stuff in the small signals because you don't have to worry about RPi path in the small signals. So usually in a lot of configurations, A0 is going to be 0 with MOSFETs, but not so with bipolars. So I have to be careful what I give you on the final in terms of the calculations. Okay, so let's just wrap up the AEQ. So for the A equivalent, we again go and do the input-output nulling to see what the load network is. So this will be M1. And now what we're adding to M1 is we'll have RS1, which is normal, RF, RS2, and then we're trying to add to the output to this network what happens when the output signal is 0. What's the output signal? Again, in this type of circuit, what's the output signal? Current or voltage? This is the output signal, right? What is it? Current, right? So if current is 0, that means that M3's source is 0, right? There's no current flowing back here, right? So if that's true, then the only thing that you can kind of add here will be RO3, because there is no current flowing back. Okay. And then we have RL1. M2, that's our standard path, RL2, Then we have M3. That goes out into the low, but now we have to figure out what network loads RS2, right? Or M3. So you have RS2, RF, RS1, and then what do we see from this point up when Vs is 0? What impedance do we see? If we ground Vs, what do we see? It's basically this situation over here, right? So we see 1 over GM. And that's what we terminate with. Okay, so yeah, if we call this R1 and we call this whole thing R2, then we can get that A equivalent is GM1 RL1 over 1 plus GM1 R1 times, or that will be a minus sign, minus GM2 RL2 times minus GM3 over 1 plus GM3R2. Right. Notice that A equivalent is in what units? A equivalent is Vs over, or it's I out over Vs, right? So it's in conductance. If I really want a voltage gain, I would have just added RL here because IO times RL is VO, right? Okay. Notice that a big part of this expression for AEQ is actually RR, right? We can see it from here. GM2 RL2, GM1 RL1. This whole 1 plus GM R1. R1 is essentially, or actually R2 is RS2 in series with RF, RS1 parallel GM1. So this R2, this whole expression is really just R2, right? So if you do some approximations, you'll be able to see that this is really minus RR times RL over RS1 in parallel with RS2. And so this could be your essentially A infinity. Or minus that is A infinity. This is minus. Okay. Okay, that's pretty much what I have with the return ratios. So next time we'll do the port stuff. And yep.
So how do we find A infinity?
So we sort of covered that just on one example, simply because it's not always that easy. But the way you would do it is you just set the A, which is, or GM, to infinity. That's right. Then it becomes a little bit tricky because you have to think of implications of that rather than going and explicitly solving. For example, the implication of we did that for the bipolar case, right, where we said we had this feedback, which was sorry, this was RF, right, and then we said, okay, the way I find A infinity is I set GM to infinity. Well, if GM is infinity, but I'm getting finite outputs, right? Because then this voltage must be 0, right? So then all the current essentially goes through the RF. Nothing goes through RPi. Right? And from that, I can analyze the circuit. But I have to use this assumption, then infer that this is going to be 0, and then start doing the analysis. Right? And that's what's harder about this method than the A equivalent. In A equivalent, you just say, I kill the input, I kill the output, I create the loading networks, and I'm done. Okay? But some people may prefer this. So that's why I'm teaching you all three, so you can get enough tools to do what you think is easier. To me, there's nothing easier than AEQ, but that's just how I do it. OK? Thank you.